In this video, we'll discuss repetition in Scheme. So repetition is what makes computers useful. Without repetition, the computational power of a program would be a function of the length of that program's text. The program text would take up as much space to write as the program could ever use, so in a very real way, repetition is what makes computers useful. Now, the two principal ways of accomplishing repetition are iteration and recursion. So imperative languages tend to use iterative features like loops, whereas functional languages tend to support recursive language features like function calls, nested functions, and tail call optimization. Something we'll discuss in today's video. So in today's video, we'll talk about recursive procedures in Scheme and the difference between recursive and iterative processes. So I want to make a distinction right at the top here between the program, the text of your code, and the process, which is the ephemeral execution of your code. Okay, so we'll discuss recursive programs, but then we'll discuss iterative and recursive processes. So the difference between those two things will become apparent. So to root all of our discussion here, we'll use the definition of a factorial. So factorial, as we can see here in our standard definition, n factorial is n times n minus 1 times n minus 2 dot all the way down to the value 1. Or equivalently, we can express this recursively by saying n factorial is equal to n times n minus 1 factorial. And then, as a base case, 1 factorial is just 1. Gives us an endpoint to that repetitive or recursive process. So if we wanted to code this in terms of a recursive procedure, just go to our Dr. Racket here, we could do so pretty straightforward. In order to create a recursive program, we need to have a base case and some sort of recursive case where that recursive case will modify its active values so that it eventually reaches the base case. Okay, so we'll say define, what we're going to call this one. Call it factorial of n. Right, and then for this we need our base case, so we'll have an if. And the base case from our definition here is if n is 1, then 1 factorial is just 1, so we don't have to do any recursive math to figure out the value. So if n equals 1, then just return 1. And in all other cases, return the current value of n times the factorial of n minus 1. Okay, so to see how this process works, let's consider the situation of factorial 5. Let's walk through the substitution model. So the substitution model for factorial 5 looks like this. We start with factorial 5 as our initial expression. We can evaluate both parts of that. So this is the function that represents all the stuff that we just described there, and 5 is just an integer. So then we do the apply step where we say substitute 5 for n throughout the body of factorial. So the body of factorial, it's two parts because there's an if statement in the middle. Because n doesn't equal 1, we're just going to jump straight to the body, the active branch in the body here. So we'll say this is the relevant part of the body of factorial. 3 open and 2 close. Let's add one more close bracket, where the value of n is substituted with its argument 5. Okay. And then if we want to evaluate this expression using applicative order, we say, okay, well, this is the time symbol. It means multiplication. This is the integer 5. And then the value of this sub-expression needs to be determined before we can apply multiplication and 5 all together. So to figure out the value of that, it's very similar to what we just did. First, we need to find out what's the value of this. So just take this one step at a time. 5 minus 1 gives us 4. And then we take this body and we replace it with, again, the active body or the active branch from the factorial function. So n times factorial of n minus 1, where n is 4. Like that. And we can speed this process along a little bit. So just say 4 times factorial of 3. And then that becomes, you can see pretty clearly in our minds, hopefully, 3 times factorial of 2. 4 close brackets. And then that becomes 2 times the factorial of 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then finally we have times 5, times 4, times 3, times 2. And the factorial of 1 is finally our base case. So the active branch there is just 1. So we can just put that there. 1, 2, so 2, 3, 4, 5. Okay. Right. And then from there, it's just math. So we start collapsing all these things. We got times 5, times 4, times 3 of 2. And then times 5, times 4, 6. Times 5, 24. And then finally 120. So the substitution model for the recursive process has this sort of deferred operation situation where before we can figure out what the result of this multiplication is, we need to figure out all of the different parts of that, so we need to expand. And that expansion leads us to further expansion and further expansion and further expansion to the point where the entire expression is laid out before any of the actual operations complete. Okay. Anything else I need to say about that? So this is what's known as a linear recursive process. Okay, so it's got a recursive function, which a function is calling itself, so it's a nice recursive program, but the process itself follows that same pattern where we have these deferred operations. Okay, so the key to this, to a recursive process, is that we have deferred operations. We're building up a bunch of deferred operations on the call stack. We have our substitution model expanding before finally completing all of the intermediate steps, and then it can start to contract. Now, sure, let's see the call stack for that real quick. So the recursive call stack looks something like this. So we have our recursive process. Call stack starts with the global and primitive scopes, and we have in the global scope the factorial function defined. So we call a factorial of 5, so we get a new activation record or a new block on the call stack where the parameter n has the value 5. And then we say times n of factorial n minus 1. So before we can figure out what the value of that is, we have to call factorial of n minus 1, which is factorial 4. Before we can figure that out, we call factorial 3, and then factorial 2, and then factorial 1. And it goes all the way down to the point where now we've hit our base case. So when we call factorial 1, we can compute an answer without any further function calls. So at that point, we can return the value 1, and that top block off the stack can disappear because it's done. So that returns 1 into this previous call, which was times 2 of factorial 1. So now we have times 2, 1, which is 2. So this can return 2 to the previous block. Now we multiply that by 3, so we can return 6 to the next block. 6 times 4 is 24, and then 24 times 5 gives us 120. So we build up a whole bunch of deferred operations on the call stack. Once we finally get to that base case, the values start collapsing down the stack until we reach the global scope again with our final answer. Okay. So in terms of understanding a recursive process, it'll help to see the difference. What's an iterative process different from this? Because I believe the recursive process probably seems pretty familiar. So to solve the same function, a factorial problem, using an iterative process it's akin to solving it just using a loop. Rather than using a recursive function call, how would you compute n factorial just using a loop? Well, you'd start a loop probably at 0 or 1, probably 1 considering 1 factorial is our base case. And then you'd say from 1 to whatever value, 5 in this case, we'll just multiply all the values. So 1 times 2, and then repeat times 3, and then repeat your loop times 4, and repeat your loop again times 5. And you just have a running counter or a running total inside that loop that's building up with each iteration, and when the loop is done, you have your final answer. In functional programming, however, we don't have for loops or while loops built in. So we need to use recursive programs to essentially simulate this iterative process of a loop. So what we'll do is we'll use a counter and a running product, not unlike our loop. So our loop would have a loop variable, I usually, would be our counter, and then some total that's going to be built up through the different iterations. So let's try solving this. Define factorial n. Now I'm just going to give this a different name. We'll call it factorial 2 just to be separate from the recursive factorial that we defined up there. But the way this works, and I'm just going to start coding things for us, and we'll see how it all comes together. Actually, the code, I believe, is in the notes right here. There it is. So factorial here it's going to be built in sort of two functions. We have our public function, which is asking just for factorial of a specific number, and then we have a helper function that's going to take care of essentially the loop process. So this helper function, we'll call it define factorial iteration, or facit for short. We'll have a product and a counter. or rather, I prefer counter and total. So this will be a little bit different than the version in the notes, but same idea. All right, so if we have a counter in our total, where counter here is just a counter that's counting up from some base value, and the total is the running total that's building up or accumulating values over time, we still need to have two cases. We still need to know, are we done this iterative process? So we have an if situation where we say if the current value of counter is greater than the final value for the counter. So we want to count from 1 up to 5 in the case of factorial 5. So n here is a free variable inside Facet. So we can just say if counter is greater than n, well then we've reached the end of that loop. So at that point, since we've been building up this whole total, we can return total. Now if this doesn't make sense yet, don't worry about that because we will repeat through this. It seems a bit strange because now we're starting by talking about the end of the process, right? So when we've finished counting up all the way from 1 to n, we'll have all the work done, so we'll return total. Until that happens, though, we need to actually do the work. So as I mentioned, we'll have to use a recursive program. So we have facit here. But what we're going to do is compute the values for the next step or the next iteration of our quote-unquote loop. So if the current value of the counter is 1, the next value should be 2. So we'll say plus counter 1. So we're going to take the current value of counter, we're going to add 1 to it, and we're going to pass that into Facet. So that's going to go into the next instance of this function call, where the new value of counter is 1 greater than the old value. Similarly with total, that's our running total or our running product. We want to build that up one value at a time, so that would be essentially 1 times 2 times 3 times 4 all the way up till n. So we have the current value of counter would be those different values. So we just multiply the current value of counter into our running total. So we'll say total is total times counter. And that goes into this new parameter on the next iteration since we're passing that into Facet here. All right, so we can close all of these. So that's our helper function. And below that, we need to initialize that helper function. So we're still in the body of factorial 2 here. What needs to happen here is we need to start this process and provide initial values for counter and total. So since we're counting up from 1 to n, the initial value for counter should be 1. And since we're doing multiplications at every step, the initial value for a multiplication here should also be 1. So we can say call faciter with 1 and 1. Okay, so this is, you can think of this as initializing your loop. This is the process of your loop. This is the end condition for your loop. And then there's you returning the result when it's done. So let's test this out. Let's see that it works first of all. Run our code. Okay, so that's the factorial n up here. And if we ask what is factorial 2 of 5, we get the same value. Wonderful. All right, so as I mentioned, this uses block structure and lexical scoping. We have this variable n as a free variable throughout this inner function. It's a pretty common pattern when you see iterative processes. Iterative processes designed as recursive functions, that is. So notice this is a recursive function. We have a function calling itself, but it creates an iterative process, and we'll see that when we see the substitution model. But I just want to describe the code first off here. So yeah, we have this free variable n, which is being used inside Facet to be the end of our counter. And that just saves us having to pass in, it would be 1, 1, and n, and then it would just sit there unused the entire time. We'd have n at all these other spots. So having the free variable just saves us some typing more than anything there. Right, and as I said, this is a pretty common structure for iterative processes. It's not mandatory, but it's pretty common that you have a public function and then an inner helper function that has some extra variables, oftentimes a counter and sort of an accumulator or a running total that's going to be building up until we reach our end point here. So the helper function here is really just used to add those two extra parameters. So we have counter and running total that we don't want the user to have to call Facet 1, 1, n every time, right? We could just give this to the public as their way of doing factorials, but then they always have to know to use these initial values. So by tucking that into a helper function, we can provide a nice convenient interface to the user where they just say factorial 5, and then we supply all the extra required helper values to do the actual process. All right, so let's see the substitution model. Let's see how this is an iterative process, even though it's using a recursive program. So this is the substitution model for an iterative process. And this is a substitution model for a recursive process. So the iterative process starts the same. We have factorial 2, just because that's the name of our function, at the value 5. We're still using applicative order. That doesn't change. But if we call factorial 2, well, that goes to here where n is 5. We get the body of all of this. I'm not going to bother writing that out because it's just going to be very exhaustive in the substitution model. But we define some sort of function called facit where it needs 2 parameters and the free variable n has the value 5. And then we get the actual body of factorial 2, which is this call here. Facit 1, 1. And there's no parameters in there, so we don't have to do any substitutions. But in our minds, we should at least remember the substitution should happen for this. If you feel like being exhaustive, you can type out the entire body of factorial 2 and make those substitutions initially. That will save you making manual mistakes later on. Right now, I'm going to remember that n is 5 when we reach it later. But if you want, you can place it directly in your substitution model. It just makes for a very bloated model, in my opinion. OK, so when we call facit 1, 1, that then goes to this function here, facit with counter equals 1 and total equals 1. We have an if statement, and as I've mentioned before, to simplify if statements, we just jump straight to the active branch. Since counter is 1 and n is 5, this is going to be false, and we'll just take this active branch here. And then we do the substitution. So counter has the value 1, total has the value 1, and counter has the value 1 again. That closes facit. OK, good. So then just to simplify this, we get facit 2 and 1. OK. So notice we're back down to a single line. So we have facit 1, 1. Now we have facit 2, 1. And that goes back up to the top. Again, this isn't true, so we have this recursive branch here. So we get facit plus 2, 1, and times 1, 2, where 1 is total and 2 is counter. We close those, simplify before we can apply, and we get 3 and 2. Right, and then we can continue on. So facit 3, 2 gets another line where we have facit plus 3, 1, and times 2, 3, which simplifies to facit 4, 6. And we get that again here, so we get the next line would be facit plus 4, 1, and times 6, 4? 6, 4. Total, counter. OK, and that simplifies again, so facit 5, 24, which then goes back to our recursive case again, so we get counter plus 1, so counter is 5 plus 1, and we have total times counter, where total is 24 and counter is 5. And we can simplify that one more time, so we get facit 6, 120, and now when we make this call, 6 is greater than n, because n was 5, so this is true, and we just use the active branch total there, so this becomes 120. OK. So there's different edge cases you could use. We started counting at 1 and went till greater than. You could start counting at 0 and go to equal to. But in this case, for factorial, it makes sense to start at 1 because that's the active value for our base case is 1. If you had a base case of 0, maybe it would make more sense to change your edge cases a little bit. But in this case, this works out. So the key difference here is that we don't have deferred operations. When we call this iterative facit helper function, we're providing all of the new values directly to it. We're never saying take the value of facit and then multiply what comes out of it by some value, right? We don't have an extra operation out here times n of whatever. Right? So that creates an iterative process where all of the information that we need is provided into the next instance of that function. So the substitution model collapses down. And in fact, for a proper substitution model, you wouldn't even necessarily need all these extra steps. This makes it pretty explicit, having all the addition and multiplication steps, but to really highlight the process, you might say something like this: factorial 2 of 5 becomes facit 1, 1, which then becomes facit 2, 1, which then becomes facit 3, 2, which then becomes 4, 6, 5, 24, 6, 120, and then finally the answer. Right. So this would be considered a valid substitution model for this example. It's a bit reduced because you are skipping a few extra steps of the actual math, so there's opportunity for error to be sure. So both of these would be considered worth full marks on an assignment or test. But the key difference here is quite very clear when we take a look at the substitution models between the iterative process, where we just see this essentially just a column of values changing through time, versus the recursive process, where we see a bunch of deferred operations building up on the call stack until we finally reach that base case. Then all of the math occurs. So with the iterative process, we're doing the math with each step. With the recursive process, we're waiting until we're ready to have all the information, then we can do all the math steps. Right. So the key to iteration is that it's based on what's known as tail recursion. So the idea behind tail recursion is that recursion is the last thing that happens in the function, right? Both of these are created using recursive functions, a function calling itself. So the recursive program in both of them works similarly, but the key difference is in recursive processes, we have work left over. So this instance of the function call isn't done until the subsequent instances are all complete. Then we have to come back, use those values, and do some extra work with them. Whereas in an iterative process, this instance of the function call is fully done at the point of function call, right? There's no more work left over once we make this function call. So there's no deferred operations, and the result of this call is the result of whatever this recursive call will be, right? The result of this instance is going to be whatever this returns. We're not going to change it once it comes back. This leads to something called tail call optimization, which means we can optimize this function call to run in constant space. Rather than building up a call stack with a bunch of new frames, we can replace the current frame with the next one because the current frame has done all of its work. We can just pass all that information into the next call of Facit and then not have to save this block for future reference. Okay. And if we pass the dynamic link to the called procedure, that is to say, if we tell the calling Facit who called us, then when they're done, they can actually just return back to the calling procedure and skip all those intermediate steps. So Scheme uses tail call optimization, which makes these iterative processes very efficient. And in fact, let's just see that on the call stack here. So we had our recursive call stack here, and it built up a bunch of deferred operations, got to the base case, and then started collapsing down and doing the math. In the iterative version, we start again in the global scope with our factorial function defined. I suppose this should be factorial 2. So factorial 5 gets called. So we get that public function with n equals 5. But then that public function calls Facit, and it provides the initial values for counter and total of 1 and 1. So we get Facit with counter and total both being 1. Now, this does all the work that it needs to do. It says the new value for counter is counter plus 1, the new value for total is total times counter, and then it says call Facit with the new values, which would be 2 and 1. But at that point, this activation record is done. It doesn't need to do any more work. So we can optimize by saying get rid of this version and then put the new one in its place. Okay, we have all the values, we passed all those values in, we cleared off this the old activation record, and the new one takes its place. And the same thing happens. We say, okay, well, counter becomes counter plus 1, and total becomes total times counter. So get rid of this and replace it with the next one. So we have the next values. And we do that again, and again, and again, till eventually we reach our base case. At that point, we have our total. Our running total has been built up through these subsequent calls, and we can just return it. So counter here is too big. Actually, that should have been a 6. Counter here is too big, so we can return the value. And at that point, the entire process is complete. So we return that back to whoever called the initial function, and we're done. Notice it didn't have to return through factorial 4, 3, 2, 1. It just went right from factorial, what should have been factorial 6, and returned back to the public function. At that point, the whole thing was done. So the iterative processes, they replace previous calls with the new existing calls because the previous calls are done all of their work. There's no deferred operations that need to be maintained on the call stack, so we can get rid of those blocks, save ourselves some space and a bit of time. So syntactically, let's go back to these things. Syntactically, both of these things are recursive. Both of these programs are recursive. The functions will call themselves. But semantically, the first procedure makes a recursive process. The second procedure makes an iterative process. Okay. Yeah, I think I said all those things. So, in other imperative languages you might be familiar with, we have the ideas or the options of using recursion or iteration. Just we have loops for iteration and function calls for recursion. And there's a big difference in those languages between using a loop and using a recursion. Right? If we create an infinite loop, what happens? Well, that loop will run forever. No problem. So, well, maybe not the greatest situation, but if that's what we intended, the code won't crash, it'll just run forever. But if we create an infinite recursion in Java or C or similar languages, it will eventually crash your program. Specifically, because each time we add a new call stack or a new block onto our call stack, we're filling up the call stack, which is taking up some space in memory on our computer. And once we've used up all of the allocated space, the interpreter or compiler or whatever language we're using has to say, okay, there's no more space for more function calls, so I'm going to crash this process. Okay. So loops require no extra memory because they just have a set number of variables and they're repeating the changes to those variables, but recursion incurs overhead with each call, which can lead to stack overflow. So let's see an example of just that. So starting with the recursive process, so let's define a function here, define recursion +1 recursion. So it's a recursive program because recursion is calling itself, and it's a recursive process because it has these deferred operations. We're going to add 1 to whatever comes out of this recursion. Now, because there's no base case, it's an infinite recursion, so technically we're never going to be able to do these additions, and instead they're just going to build up space on the call stack. So what happens when we run this program? Call recursion. Program starts to run. Many different recursions over and over again. This could take a little bit of time because I have a pretty big system and it's a pretty small program. And there it goes. The whole thing runs out of memory. So eventually, this whole thing fills up the call stack with a bunch of very small activation records for each instance of this recursive function. And because there's still this deferred operation +1 to whatever comes out of this, we don't have the ability to get rid of any of those activation records until we reach the non-existent base case. So we fill up the call stack, and eventually we run out of memory for new activation records. Okay. Now, if we want to compare that, though, to an iterative process, define iterative. This needs just a variable to keep them similar in kind, and this calls iterative on that variable +1. So, same idea as the recursive program. We're going to repeatedly call this function over and over again, but instead of deferring the addition operations, we're going to do the addition on the way forwards, or on the way up the stack, if you will. So let's run this program and see what happens. So if I call iterative with the value, any value will do, the program starts running. You see this little man going. Notice there's no memory changes happening whatsoever. It's just running and running and running. And if we leave this overnight, he'll continue to run because he's not using up any extra memory. So what we have here is effectively just an infinite loop. And that's it for this video. So we covered recursion and iteration. We saw the difference between programs and processes as well. In the next video, we'll go into a different kind of recursion known as tree recursion.